Welcome to the Phenomenological Alliance channel. In this video, we will emphasize the distinction between theoretical models and real human experience.
The nature of the gravitational field is a major area of investigation in contemporary physics and astrophysics. Theoretical physics from the late 19th century through the 20th century has been characterized by the exploration and development of the concept of gravitational waves. Following the acceptance of Maxwell's theory that light is electromagnetic in nature, it became widely accepted that all other forms of radiation are also electromagnetic waves, differing in their spectral ranges compared to visible light. Thus, the scientific community accepted that infrared radiation is a form of electromagnetic oscillation with lower frequencies than visible light, while ultraviolet radiation covers the electromagnetic spectrum with higher frequencies than visible light. In this division, gravity remained unclassified, despite some opinions suggesting it was electromagnetic in nature. The acceptance of the electromagnetic nature of gravity was restricted by Newton's model, which required gravity to act instantaneously. Any delay in the propagation of gravity would lead to the universe's collapse, a problem Newton was fully aware of.
I reckon this is as hard as to make not one needle only but an infinite number of them, so many as there are particles in an infinite space, stand accurately poised upon their point.
The concept of gravitational waves was initially proposed by Oliver Heaviside in 1893 and subsequently by Henri Poincaré in 1905. Given that all other forms of radiation demonstrate oscillatory properties, it seemed logical to assume the existence of a gravitational counterpart to electromagnetic waves. In his theory, Poincaré, unlike Newton, posits that gravitational waves propagate at the speed of light. Shortly thereafter, Einstein integrated the theory of gravitational waves into his relativistic model. Einstein demonstrates his ideas through mathematical formulations, building upon concepts such as the universe's total matter and energy, the cosmological constant, the law of an expanding universe, and related theses. From these premises, calculations suggest that the geometry of space and time is shaped by the presence of matter and radiation. Gravitational waves are notoriously difficult to detect, requiring highly sensitive equipment. Contemporary experiments utilize laser interferometers. Essentially, a beam splitter divides coherent light into two beams that reflect off mirrors. These reflected beams then recombine, producing an interference pattern that can be analyzed. Experiments for detecting gravitational waves aim to detect how gravitational wave radiation influences the light beams in interferometers. Analyzing interference fringes is expected to reveal the true nature of gravitational waves.
Let's conduct a phenomenological analysis of the stated positions. The idea of light waves traces back to 1665, where Francesco Maria Grimaldi proposed that under specific conditions, light can cancel each other out. This idea eventually led to the widely accepted conviction about the existence of light waves, a notion demonstrated by light interference experiments. One way to achieve light interference is with the help of so-called diffraction gratings.
In optics, a diffraction grating is an optical grating with a periodic structure that diffracts light or another type of electromagnetic radiation into several beams traveling in different directions. A diffraction grating is a surface with regular grooves, similar to those on a CD. When illuminated, it produces color transitions due to the superposition of reflected light waves.
However, these interpretations disregard the naked truth that the initial light can always be restored through focusing. The notion that light is able to cancel each other out fails to explain how pristine light can be reconstructed from interfered or cancelled light. After the optical breakwater, the analogy between the water waves and assumed waves of light ceases. Focusing light shows that a mixture of cancelled and uncancelled light recombines into an image. Regardless of theoretical interpretations of optical phenomena, the problems in optics ultimately lead back to its origin, an image. Light is an image that can be obscured, inverted, or overlapped, giving rise to persuading theoretical illusions. Regarding the concept of gravitational waves, it's important to understand that the concept of waves or oscillations is inherently connected to rhythm, specifically to repeated patterns of movement. Phenomenologically, when considering the relationship between gravity and oscillation, we are led to examine the causes of stability in rotating systems. In a double rotation system, the gyroscope stabilizes its position by moving away from the point of horizontal balance based on the direction of rotation. Conversely, causing the gyroscope to become imbalanced changes its direction of rotation. The stability of rotating systems in physics is explained by the concept of the conservation of angular momentum. This principle describes how stable trajectories form within specific points in space in double or multiple rotation systems. Newton analyzed the reasons for the emergence of forces in the solar system using the then relatively new heliocentric model. This led him to conclude that there is an attractive static force between matter. However, his analysis of the fall of the apple remained entirely within the framework of the geocentric model. The problem of the stability of rotating system, reflected in the conservation of angular momentum, are concepts that were developed only after Newton. Understanding the stability of a rotating system is inseparable from the question of why the apple falls to the ground. On the other hand, Einstein notes the similarity between inertial and gravitational forces. Unlike light and electromagnetic waves, which have entirely different characteristics, there is no discernible or intuitive difference between artificial and real gravity. In mainstream physics, it is asserted that the fundamental difference between real and artificial gravity is that artificial gravity always acts opposite to the center of rotation. But Einstein considered his thought experiment in a model with constant acceleration, not in a multiple rotation system. This oversight led him to miss that the direction of artificial gravity does not always oppose the axis of rotation. In a multiple rotation system, an epicycle forms around a stable trajectory along which the body oscillates rhythmically. In an upcoming video, we will also cover other aspects of rhythmic oscillations around a stable trajectory that are related to the problem of gravity.
Phenomenology, the science of conscious experience, employs a holistic approach to heighten awareness of both external and internal phenomena. Through this perspective, physics, physiology, and psychology naturally intersect. From a psychological perspective, stability involves reactions to changing circumstances. When performing routine tasks, we encounter fewer difficulties because we are dealing with familiar problems. However, new situations compel us to create or modify routines, invariably causing some level of stress. A person is psychologically more stable the faster he or she can adapt to a new situation. Similarly, in the outside world, objects remain stable either when they are at rest or when they move uniformly rectilinearly. When the trajectory becomes unpredictable, the response to instability also becomes unpredictable. When people get lost in the desert or woods, they become disoriented and start moving in circles, following an unstable path. Spinning in circles is a reflection of instability, both internally and externally. A phenomenological approach can recognize the connection between psychological or physiological stability and phenomena of stability related to the appearance of gravity. Since this connection is not founded on theoretical assumptions about reality, this perspective is fundamentally different from that of mainstream physics. Rather than theorizing about the physical oscillation of gravity, the phenomenological approach focuses on the causes behind the loss and re-establishment of stability in periodic motion.